about some of the things that, just to give you a bit of an orientation about where I work. There's also just a couple of things I wanted to actually just give you a bit of an update on as far as the presentation is concerned. So hopefully this will move. Yes. So the contents, just an introduction, just to give you a bit of an orientation about where I'm from now, which is in New Zealand. The facilities, the people who I work with, and just a bit of a general overview about our group as well. I also would like to focus more on the adaptive optics and wavefront sensing, specifically on adaptive optics systems that we've been developing. One of the key reasons, not the only reason, but a key reason why I was so keen to actually visit the group here was primarily because there's quite a lot of similarity in terms of the usage of wavefront sensors for adaptive optics. So that's, I think, TP3 is what you call yours, and we call ours the geometric sensor, and there's a number of advantages that I'd like to go through based on that. I'd also like to talk about the hybrid system that we are proposing. Alex mentioned about how we were provided with some funds, which is, there's a part of the Royal Society of New Zealand. Every year there's about 30 academics who are basically awarded funds for their research, and I was fortunate enough, after a number of tries, in order to succeed with funding. And this sort of works very much in line with what we're doing as far as a country, as far as our being space aware is concerned as well. And so we have Rocket Lab, and I'll talk about that a little bit as well. But Rocket Lab, so we are a spacefaring nation now, and the space situational awareness fits in very well with that. I'd also like to talk about some current collaborations that we're doing and future collaborations as well, and to close my talk. I have a lot of slides, and I do apologize if I have to, if you're interested in a particular slide and I have to actually skip a few. So I just wanted to give you the heads up, because yeah, you tend to collect. I had a lot more, but I basically had trimmed it back to the bare minimum. Anyway, let's start off. So where are we? First of all, we're in New Zealand. Where's New Zealand? If you can find it, good luck. We're very small, a little bit like the Canary Islands, in the world scheme anyway, but we do punch above our weight. And so we have, where are we? We are here, yes? And New Zealand is here. So I've tried to actually put it in the center, give you a bit of an idea, and we have various different routes, as you can see there, over the country. So we're in a fairly strategic position as far as satellite passes are concerned. Australia is where I'm originally from Sydney, and it's about a 3-hour flight between New Zealand and Australia. And we have a number of colleagues here. We have colleagues also in Europe, and colleagues in Europe who are from the ESO as well as the ESA, who we deal with, and I'll talk a little bit about those as well. Okay, so more specifically as far as our country is concerned, so this is a bit of a focus on what we're doing with regarding our situation. So I'm situated here in Christchurch, and we have an observatory which is called Mount John Observatory, which is located in the Mackenzie, what we call the Mackenzie Basin, which is in here. Number of people who visit New Zealand also like to see things like movies, from sets and scenes from Lord of the Rings, for example. And there's a number of areas around, particularly around the Mackenzie Basin, which we've basically shot. So Peter Jackson basically provided a number of scenes from that region. There's a proposed site for space situational awareness, which is a phased array, which is basically in the southern part of the South Island. So we have 2 islands in New Zealand. And the southern island is very much more sparse than the than the North Island, have about 4 million people, but this is where the proposed LEO Labs phase array is going to be installed. Further up on the North Island, we have our capital, which is Wellington, and we have a number of smaller observation sites up here, but the premier site is Mount John University, which is what we use. So it's a university observatory, and so we can use it for fairly low cost. We still have to pay to some degree, but this is our premier observatory, and 2 observatories which are further up in the North Island are smaller in scale. I'll go through those in a bit of detail. This might be of interest too. This is our the Rocket Lab launch facility, which is on the Mahi Peninsula, and we have, I shouldn't be saying this because it might be on YouTube, but there's been a number of launches that have basically put a number of satellites into orbit from the Mahi Peninsula. So I think we're about the 18th country who has space awareness and has launched capabilities. My university is the University of Canterbury, and this is a bit of an old picture, but basically this is where I'm from and where I work. Okay, so moving on. Christchurch. I don't want to talk too much about Christchurch. I want to talk more about the science. But we have a population of about 400,000, a bit over 400,000. And this is our makeup, so mainly European. And we have Maori. There's a much higher Maori percentage as far as the North Island is concerned rather than the South Island. And of course we have also a reasonable percentage as far as Asian residents are concerned as well. This is Christchurch itself. There's a very large extinct volcano, and you've seen a lot of similarities actually, particularly as far as Lake Palma is concerned and New Zealand in terms of the landscape. Certainly there's more volcanic activity as far as the North Island is concerned, but this is an extinct volcano, and it has the beauty as you would expect, and as you have here, and also on Lake Palma and the other islands of the Canaries. Okay, so I might just skip this slide. It's about University of Canterbury. Basically, this is our old campus, which is basically situated in the middle of the city. We've moved from there, but we do have some facilities there. And as I mentioned about Ernest Rutherford, so one of his laboratories is there, and if you come to Christchurch, you can visit and go through his laboratory where he worked. But anyway, there's a few other bits and pieces up there you might want to read at some your leisure. Electrical engineering is the department where I'm from, and we have about 500 students. We have about 120 postgrads. Might be a little bit a little bit less than that, but we have a fair sized number of postgrads, and there's about 20 academic staff in the department. Okay, so the observatory, which is Mount John, as I said, it's our premier observatory as far as New Zealand is concerned. We have a number of telescopes there, and I'll go through some detail about the telescopes because they're an instrument, or all of the instruments we try and use. This is the topography here is Lake Tekapo on the right, and there's Lake Alexandrina on the left. And it doesn't look like it's on a hill, but it is certainly on a hill. It's about 500 metres between the flat here and Mount John, the top of Mount John. The observatory sits about 1,000 metres above sea level, and that's so it's not particularly high in terms of altitude, but we're certainly above a lot of the boundary layer as far as around the surrounding area is concerned. So we have a 1 metre McClellan telescope. This telescope was basically added to the structure which was already here. In fact, this structure used to be a satellite station from the US, so it was actually put in place about in the 1960s, 1970s. And We have added a number of telescopes. So there's the MOAO telescope, which is a collaboration with the Chinese, sorry, I beg your pardon, with the Japanese, and it's a 1.8 called the MOAO telescope, micro-lensing events. Pretty much it's dedicated to micro-lensing events. We have a 60 centimetre optical Craftsman, and this is another telescope that I use, which is a 60 centimetre Boulder and Shivers telescope as well. Just a very brief shot of the MOAO telescope. So micro-lensing events, that's one of the main reasons why it was built here. So it's an extension to work from Nagaya University in Japan, and certainly there's been a number of publications as a result of using this instrument. And yeah, I'd love to go into more detail, but I don't use this instrument particularly. This is one of the instruments that I do use, which is the 1 metre class telescope. And this is, yeah, basically it's a Cassegrain reflector, so 1 metre in diameter. It has two different focal ratios, 7.7 and f13.5. We're currently changing the rig, the existing rig, to a multi-object adaptive optics rig, which I'll talk about very shortly. The wavefront sensors that we use are curvature and also geometric, but also we've used Shack Hartmann. Mainly we've used these in open loop rather than closed loop, but I'll talk a little bit about that part of my presentation. Some of the cameras, so currently we have fairly inexpensive cameras, but we are going to and/or instruments for the Exxon as well as the Manara, which is going to supplement, well, allow us to apply our technology in wavefront sensors to space situational awareness application. This is an example of one of the early rigs that we've designed. We're going to be enhancing that accordingly. Okay, and this is the Boulder and Shivens that I mentioned before, the 0.6. This is also used by microlensing or for microlensing type applications. And so we can see here one of the rigs. So we tend to make a distinction between the rig and the telescope, or the instrument, I should say. So the instrument that you would call an instrument, we call a rig, and the rig is basically applied at the back of the telescope. And of course, every time there's an instrument change, it has to be basically reweighted and everything else, and it's a bit of a pain, but we do have staff at the observatory in order to provide that support. And this is an example of some of our work. So our group, so we have 3 academics. We have a postgraduate fellow, or postdoctoral fellow, I should say, and we have a number of students who are part of our group. We've got probably one of the most diverse groups, I think, in a university, so from US, India, South Africa, China, etc. And we've had a number of completions here. This is only a very small snippet of those that have actually done, have completed their PhDs with us. So I head up the group. There's Richard Clare as well, who's a close colleague from the department. He's our postdoc, Vishnu and Andrew Lambert is a colleague from Australia, from the University of New South Wales in Australia. Okay, so a very short introduction to adaptive optics. Assuming here that you've got some knowledge of adaptive optics, that's probably why you wouldn't be here. We know, of course, that above the Earth's atmosphere, we have effectively diffraction-limited imaging. And basically, as the waves propagate through the Earth's atmosphere, we have phase distortion of the wavefront. And we can see here the result of that in terms of speckle imaging, so high-frequency sampling imaging. So we want to basically remove the distortion. We want to try and measure the phase, estimate what the phase is, and to correct for that phase distortion. And of course we have scintillation as well, which is the amplitude. So in this schematic, what I'm showing here is essentially the process for adaptive optics Again, I'm going to just skip through this very briefly because I realize that many of you are already aware of the principles behind it. But the fairly conventional system of using adaptive optics is to have a wavefront sensor. Can be, for example, a Shack Hartmann wavefront sensor. We have some form of controller. We take the perturbed wavefront. We basically measure what that perturbation is, depending upon how many lenslets we have as far as the Shack Hartmann is concerned. We have a wavefront controller that then will correct in real time. Okay, so it's very much a closed loop system, and you can either have a deformable mirror, or you could have, for example, a tip-tilt mirror system in order to actually remove either the high-order perturbations or the low-order perturbations. Okay, so the tip-tilt is certainly a major one because it contributes to about 70%, 80% as far as the distortion is concerned. So we want to measure the phase, and the phase is done, as I said, with a Shack Hartmann wavefront sensor typically, but not always. It can be a different type of wavefront sensor. So colleagues for example, in Europe, with the extra large telescopes, are using pyramid sensors. It seems to be the main preference as far as wavefront sensors are concerned. We've had a history of wavefront sensor design for curvature sensing. So we've extended Rodia's original curvature sensor design and enhanced that. And we've come up with, not me, but a postgraduate student who's now finished, Marcus van Dam, a geometric wavefront sensor, which has a spin-off as far as the TP3 is concerned that IOC are using. So if we want to extend this, well, first of all, the wavefront sensor, such as Shack Hartmann, so for those that are unfamiliar with it, it's basically subdividing the aperture, where we have a number of lenslets that provide effectively localized measures as far as the actual tip and tilt are concerned. So it's the slope we're looking for on a localized basis as far as the aperture is concerned. So each one of these, for example, if there are 4 lenslets, you'd actually be able to measure the wavefront from those 4, or the slope, I should say, from the 4 lenslets, and then correct accordingly. And then, of course, you have then some mathematics. You have various different interactive matrices that you actually then generate, which then provide the mapping in terms of the correction is concerned to the system. So there are a few limitations with the conventional adaptive optics, which is the system that I just outlined. So one of them is, for example, that the region of atmosphere measured is very small. So this is the isoplanatic, well, it's defined by the isoplanatic angle, or the isoplanatic patch, if you like. And depending upon what the level of turbulence is, which is typically defined by R0. Give you an example as far as Mount John is concerned, we've got an R0 of about 5 centimetres. And that means that if we're using a 1 metre telescope, for example, it's reducing the resolution down to 5 centimetres from 1 metre. So that's why we need adaptive optics. And we haven't had a system in New Zealand which has incorporated adaptive optics yet. So we're looking at basically taking quite a leap as far as our systems are concerned, and hopefully the results will be commensurate with that as well. So the area that we're looking for is very small, that we can actually measure is very small. And we typically need a reference in order to actually provide that correction. And if we don't have a reference within a particular science object, we have a problem. So we can either look at natural stars, but again, if there's no natural star near the particular science object that we want, we have to then think, what else can we do? And an obvious answer would be to have some form of laser guide star. And the laser guide stars have their own issues that I'll talk about very shortly. However, what we are looking at is effectively having some form of regions where basically satellite trajectories are going through certain regions within the night sky. And as a result of that, we can actually focus in on those particular regions. And we could be assured that there's going to be more than one reasonably bright object within that region. And I'll go into the methods very shortly. So we're using techniques, we don't need to have one bright star as far as the reference is concerned close to a particular target object. That's effectively what I'm saying. Okay. But we do need more than one star in order to actually provide some other means. So this is, I'm actually on my way to, not at the moment, but I'm next week in Delft for a conference which is the AOIM conference, and I'm presenting there some results. These are just a snippet of those results, but effectively we've calculated that based on a probability that we'll have 4 or more natural guide stars of magnitude of 9 or brighter within the field of view looking at the galactic plane in the southern hemisphere from Mount John University based on a 22 arc-second field of view. Okay? So this is essentially what we're going to be using. Now, magnitude is fairly dim, okay? So we need a wavefront sensor in order to actually provide resolution as far as the wavefront is concerned based on that natural star. And that's a challenge. And we can't do it with a Shack Hartmann sensor. Well, we can't. You might be able to, but we can't. So we need to look for a wavefront sensor that's going to be providing that particular capability for us. And I'll go into that very shortly. Okay. So what I'd like to do, and I mean, this isn't a new topic by far, but I would like to introduce you to the multi-object adaptive optics system that we're proposing, which is where we have more than one reference object that doesn't necessarily need to be near a target object. And you can have a relatively stationary target object, such as, for example, a planet or another star, okay? Or you can have a dynamic object, such as, for example, a satellite that's orbiting. And this is an example of an orbiting satellite where it's passing through a field of view, and it needs to be a wide field of view in order to encompass a number of bright background objects, natural background objects. And what I'm showing there is just basically using 3 objects here, and those 3 objects basically have a planar wavefront above the atmosphere. After it passes through the atmosphere, of course, they're going to be perturbed. Those perturbed wavefronts then are all going to be basically ending up on a wavefront sensor for a wide field of view. And what we're proposing is to basically have one star that is being used for example, an on-axis wavefront sensor, or acting as an on-axis wavefront sensor. And that is then being provided as far as the Shack Hartmann sensor is concerned. And the correction would be low order tip and tilt, which removes the majority of the wavefront. So this system would be in real time. Closed loop, as I mentioned before, is a fairly conventional adaptive optics system. However, the multi-object, where the multi-object comes in, is based on having some form of wide field sensor. And the wide field sensor would be, for example, either a geometric sensor, your TP3, or some other type of sensor that can image multiple wavefronts, or if you like, the regions of interest over multiple wavefronts, and using some other method in order to actually then calculate what the particular perturbation is over a wide field within that field. Ragazzoni, for example, talked about correcting the whole sky. We don't want to correct the whole sky, we just want to basically correct one area where, for example, if we do have a satellite that's basically moving through a wide field of view, as it's moving, we can then capture, for example, the in-focus image of that and correct that image, not in real time, but basically as batch processing. So our objective here is to provide some feedback, some information about a satellite and its condition. Okay? You have effectively these license plates also for satellites that effectively provide some indication. If you lose communication, for example, with a satellite, you need to have some mechanism in order to actually identify the satellite. And so some of these systems will require adaptive optics. So this is where this proposal is coming through. Of course, rather than Ragazzoni, there are other methods such as MAP that's used by Fisco. And I developed a machine learning method back in 2009, part of my PhD, which effectively trains a neural network using reservoir computing in order to effectively provide spatially variant point spread function, the derivation of a point spread function. So using this method, machine learning method called reservoir computing. So two wavefront sensors, one removing the low order, and the second, which is providing the multi-object in order to actually then extend the isoplanatic patch to a wide field. So I think the next schematic provides a bit more orientation about how that works. I'm sorry about the definition of the graphic there. But effectively, we have what we saw before as far as the natural background stars are concerned. There's a target, like, for example, a satellite moving through a wide field. And the more orthodox methods, such as atmospheric tomography that's being used, that was developed by Ragazzoni and subsequent authors, effectively provide then the measurements as far as the overlapping of each projection of the aperture to the actual reference object, and basically you can feed that information into using matrix manipulation and various different techniques in order to estimate what the perturbation is of an object as it's moving through a wide field. That's one method. For my PhD, I effectively just use one layer, one strong layer, rather than multi-layers. And I have extended that in publications for multiple layers as well. But effectively, we provide some form of training for a wide field for the perturbations in terms of phase screens. And this is an extension showing the Ragazzoni method using tomography, which effectively looks at or uses the metapupil, which is shown here, as far as then the derivation of any particular area within that region. So I'd refer you to Ragazzoni's paper in Nature in 2000. Some of you might be familiar with that, but that's effectively one of the methods that we could use. We are proposing a different type of method that I'll go into very shortly. So the other method, of course, is using deconvolution from wavefront sensing, which is open loop, and this doesn't necessarily need to be in real time. And effectively, what we're doing is we're using the wavefront sensor. We're measuring the perturbations from the wavefront sensor, and we're basically using those in conjunction with the perturbed image in order to deconvolve that perturbed image, so we can then estimate what the image should be. And that is also part of our system. So if we look at, for example, another schematic which provides, this is from my from one of our papers, where we have, for example, a number of background stars that we're using as far as references are concerned. We've got a science object, not necessarily in the center. It doesn't necessarily need to be in the center view. It could be anywhere within the field of view. This feeds into either extended curvature wavefront sensor or a geometric wavefront sensor or a TP3. We have the outputs of those which we have imaged, Z1, Z2, and Z3. They feed into a modal predictor network. So this is something, again, that I've developed. The output of that is an estimate of the point spread function. If we also include, for example, angular separations between each one of these source objects and the target object that we're looking for. So based on that information, we can then extract the point spread function, which is spatially variant. So this point spread function is spatially variant pretty much anywhere within the field of view, and then apply a deconvolution algorithm based on the perturbed image, which is G of t, in order to then extract an estimate of what the image is. So this is the system that we would like to implement. So a hybrid adaptive optics system is what we're proposing, where we have a AO loop, which is low order aberration. We have a high order, which is done offline. And we have a deconvolution from Wavefront Sensing, which then provides an estimate of spatially variant point spread function, which is h. So this is the approximation of h. And then we apply that to the image, and then we estimate what the object is going to look like as far as restored object is concerned. A few issues. A number of things that we have provided, particularly as far as the characteristics of the atmosphere are concerned. So what's not shown there but should be shown there is various different conditions, prior conditions as far as the atmospheric characteristics are concerned. Now, they change. So over a night's viewing, you'll have a number of different changes throughout the night. And so we need to actually look at the temporal coherence of the atmosphere and make those modifications as a result. And so we have stability issues as far as the processing is concerned, and obviously our modeling only goes so far. We need to then look at how we can actually then compensate for what we don't know at the moment as far as our models are concerned. So wavefront selection for multiple object adaptive optics is very important. And there's a few wavefront sensors. This isn't the entire list, obviously, but some of the more popular wavefront sensors that we've used. You probably recognize, of course, the curvature, the pyramid, and some of the shearing interferometers. There's a holographic wavefront sensor that probably not many of you are aware of, but it does exist. There's been quite a bit of work done in the States, and also colleagues over in New South Wales, University of New South Wales in Sydney, in Canberra I should say, have actually done quite a bit of work and published accordingly on these holographic wavefront sensors. By the way, I think my details are on the first slide, so if you're seeing this this video and you want to basically send me a request for these papers, please feel free. I'm only too happy to help you in that regard. So contributions, of course, are not restricted to the Shack Hartmann sensor. There's been contributions in the geometric sensor, so Van Dam, as well as myself, in terms of applying wavefront sensor technology to a wide field using machine learning. The TP3, which is also being used, of course, and has been successfully used as the first wavefront sensor, the geometric wavefront sensor, or base geometric wavefront sensor on Sky. So we have used the geometric in open loop, but not in closed loop, but ISC has used it in closed loop. And of course there's the image plane techniques as well. So there's a number of other techniques that could be used. We see the geometric or the TP3 as being fundamental for our use. and really looking at some of the, the basics here, with a Shack Hartmann sensor, of course, it depends on the number of wavelets you have in terms of these discrete changes in terms of each lensnet. So each one of these lines would represent a lensnet. Whereas for a curvature sensor, geometric sensor, there's more of a continuous curve, okay, that we're actually deriving. Now, in actual fact, of course, it's not entirely a curve. You've got the pixelation, you've got a number of other aspects as far as the wavefront sensor is concerned with the CCD or SCMOS device. So it's not perfect, but hopefully you can see that there are some significant differences here. And the linearization is also an important part. We want the relationship between our measurements and the actual wavefront to be linear. So that's a fundamental requirement. Localization, the measurement must relate to a region of the aperture, and it must be broadband as well, or for our use anyway. So the sensor should operate over a wide range of wavelengths, and we've tested that. Principle behind curvature sensors, it's a very simple system really. We just have two defocus planes. So we have an inter and extra focal. So if this is going to be the focal plane here, this is our wavefront aberration. Basically, if we have a planar wavefront, then we have equal intensity on the intrafocal and also extrafocal plane. So intrafocal here and extrafocal here. This would be showing that there's no aberration as far as the system is concerned. If we have a defocused aberration or a focal aberration, then that focal aberration, if it's going to be positive or negative, in terms of a Zernica polynomial, for example, it will shift the focal point, and therefore you will actually get either a lower intensity, smaller, and a higher intensity, smaller representation on the intrafocal, and conversely you'll have a dimmer but wider on the extrafocal. And of course, because of the conservation of light, you're not going to lose, well, you are going to have a small loss, but generally what you have as far as a planar wavefront is concerned, the energy is going to still be retained within that particular configuration. And that's the basis, or one of the bases for the geometric sensor, of course, as well. So, two defocus planes. This is a similar type of schematic showing what the next steps are in terms of providing the curvature. So we can see here that we can then do an estimate as far as the slope is concerned using the integral of S of x in order to actually then measure what the curvature is going to be in terms of, in this particular case, it's going to be a defocus aberration. Part of my work, my PhD work, started off looking at multi-object adaptive optics, and so this is a schematic of two wavefronts over a wide field of view, and I showed in the laboratory how we can actually represent that and extract the wavefronts from each one, and using the geometric sensor. And we can see here that, well, in fact, the reason why this is so coarse is because we actually used a spatial light, or I used a spatial light modulator, and rather than some form of deformable mirror. The spatial light modulator was quite a useful tool in order to actually show that the method worked. We've published accordingly. So there's a few trade-offs. I mean, photon count is always an issue. One of the big advantages of the particular wavefront sensor that we're using is that it's very sensitive, and as distinct to a Shack Hartmann wavefront sensor. And to estimate a high number of modes, you need to have good resolution in the pupil plane. Okay? To make the estimate accurate, okay, you need good resolution in the image plane. So there's trade-offs there. Some of the results, as far as simulations are concerned, show that where you have subdivided aperture, and you have, for example, variations as far as R0. And if you recall, R0 is the parameter that we're using as far as measuring the amount of turbulence is concerned. You can see here that as the turbulence changes, we have the mean squared error changes accordingly as well, okay, in terms of the amount of turbulence or the R0 parameter. The curvature sensor signal is represented here, so we've done some simulations as far as the intensity measurements are concerned, and it gives an approximate estimate of the curvature. So the two planes also are used for the curvature sensor in order to reduce the effects of scintillation. Although interestingly, Ragazzoni in his paper, 2000, the Nature paper, only used one plane, used two planes, and argued that for mild turbulence, you can get away with only using one plane because the effects of scintillation aren't overpowering. There's some debate about that. He did show that there's an average as far as the effectiveness of the method is concerned, which I suppose is why it's in Nature. But yeah, to get good results from highly turbulent conditions, you really need to remove the scintillation, and that's done by removing the extrafocal from the intrafocal. So trade-offs, wavefront sensor, sensitivity dictates the movement or the moving of the detector planes towards the focal plane, and the aperture resolution, which dictates the planes, should be closer to the aperture. So you've got basically a trade-off there with that sensor. Geometric is not as prone to these sorts of issues, and this is why it's our wavefront sensor of choice. And so the intensity distribution of the probability density function you can see here, and as the wavefront propagates, the PDF evolves. So we take the cumulative distribution function, and that also changes as well. Now, in addition to this, of course, we need to take a slice of the wavefront, and what's typically used is the rate and transform to do that. So we can see here the rate and transform being applied. It's been used for medical imaging for many, many years. So this is what we use, and I believe this is what IAC uses as well. And when we do that, the two propagated images here, another example of how that could be done. We've also got the irradiance transport equation that shows the derivation mathematically as far as the relationship of the geometric optics, even when there is scintillation. And we can see here that there's a cumulative distribution function which matches the two intensity distributions. This is how we work out what the slope is, or based on the slope. Now, putting all that together, we get a result. And the result is, as you can see here, a reasonable match as far as the actual perturbation is concerned, the phase, which is what we want, because, of course, this is what we want to output to the system in order to do the correction. So comparison with the Shack Hartmann sensor, as I mentioned before about the number of photons that are used, the Shack Hartmann needs basically more light than the direct slope or the curvature sensor. We can see here that in terms of the performance, when there's very few photons, basically the mean squared error is significantly lower as far as the slope converters are concerned. Now, the problem, though, with a number of these wavefront sensors is using the slope method, which is the geometric and TP3, is computational intensity. Now, I realize that your group has actually used a GPU in order to speed things up. That's great. We haven't done that. What we've looked at is using some methods such as, for example, ridgelets in order to represent the wavefront in a different way. Okay, so these are ridgelets which are basically based, or which are essentially based on the MOAO wavelet. So it's a 3D representation. And when we actually substitute this particular signal processing transform into the process, we could represent the wavefront using ridgelets and use the ridgelet transform before basically going through the process of then deriving what the cumulative density function is for the inter and extrafocal, and then coming up with the histogram representation in order then to estimate what the Zernica coefficients are. And we've had some success in this. We can actually reduce the CPU by, or the computational complexity by about 50%, which we think is very significant. Looking at the time here, so I'm going to wrap up pretty soon. The advantage of doing that, though, is that we have also made the wavefront sensor more sensitive. Okay, so we can see here some simulations, and this is a published paper. I think it's an SPIE paper. And we can see here that there's the more orthodox geometric sensor wavefront sensor method here. In terms of the RMS, we see here that for the same amount of light, we can then significantly reduce the amount of, or have a more effective use with low light, under low light conditions with the ridgelet-based wavefront sensor. Okay, getting to there now. So our proposed system, and we're having this built at the moment for our 1 metre class telescope at Mount John that I mentioned before, is where we have a hybrid system, where we have, for example, our in-focus camera, we have our tip tilt camera, which removes, using the adaptive optics system, the low order aberration. And then finally we have either a TP3 or geometric wavefront sensor, which is using your lateral displacement beam splitter method over the single camera. Okay, so that's effectively what we're proposing for our system. Now, the first phase we're currently, we should be testing on Sky when I return next month to New Zealand, which will be the tip tilt camera, etc. System here. And as I mentioned, we haven't actually had a 1 metre class telescope using an adaptive optics system before in New Zealand, so we're quite excited about actually publishing some results about that. So say space situational awareness, I mean, this is part of the title, my title, for this talk, but ultimately this is what we want to apply it to. So not only make the telescope's image better, but also of general astronomical objects, but also be able to provide it on extended objects such as, well, just as a comparison, the International Space Station is about, what, 109 metres, okay, in length. It's huge, jumbo jet size. You wouldn't even be able to see a CubeSat here as far as it would be sub-pixel, so there's no way, okay. So there are other methods that we're working on in order to bridge the gap between these two sizes of extended objects that we would like to view. And obviously there's geostationary satellites and others that we can actually use in the meantime, but we are aiming to try and get to CubeSats as part of this research, at least outline. See how far we get as far as the improvement of resolution is concerned. Collaborations, existing collaborations are with the University of New South Wales, as I mentioned, in Canberra. And so there's some of their results as far as using light curves are concerned. They have a Falcon telescope that they basically use, but they also have their own technology, and they actually build their own cameras as well. So my colleague, Associate Professor Andrew Lambert, heads up the group, and they have a number of postgrads and also postgraduate students as well. Lastly, let me just close on some of the other work that my colleague mainly is involved with, which is Richard Clare. So he's working with the ESO on extra large telescopes, and particularly looking at the wavefront sensor or using the wavefront sensor. We've just purchased a reasonably high cost spatial light modulator for this particular reason or method, in order to actually then provide different types of configurations and orientations with the spider. So as we move the spider around, for example, we can then match up the various different sectors of the mirror and look at the perturbations or the various different harmonics that are created as far as that is concerned. So we have at least one student working on that at the moment, who in fact I think visited your group last year. There was a conference last year, and and these are some of the results that he's got within this paper. Okay, well I might wrap up there. I've only got a few minutes left, I know. After the 50 minutes I think I've probably gone over time a little bit. But I might open it up for questions at this stage, if that's all right. Yeah, that's great. Yeah. Thank you very much. Thank you.
Questions here and someone? Everyone understood everything?
Or rather than questions, any comments?
Waiting to take the scientific coffee. Okay, here's one.
Hi.
It's for the streaming that we...
Okay. Hi, Steve. I have two questions. One is, what's the condition of the scene for the mid-June? I think, June. I think the observatory
scene
in New Zealand.
in New Zealand?
The scene.
The
ceiling.
It's not very good, I'm afraid. It's about 1.2 arc seconds.
1.2 arc seconds. Yeah.
Yeah.
Let me see. So
Yeah. It's got a long way to go before it gets as good as yours. But what about 0.35 or something?
Yeah. Another question
so
is.
it's challenging.
Yeah, thank you. Sorry. Another question is, if I understand correctly, that for multiple object adaptive opticals, one thing is just to measure the wavefront error in three-field view and correct it with open loop. Another thing is just can measure the PSF and just recover the image offline.
That's right.
So my question is it necessary to correct it in real time if we can get the corrected image offline?
Yes, and definitely to be able to correct in real time without having to go to a batch process would be our preference. But at the moment, computationally we can't do it. We don't know how we can do it, and so we're working on that particular problem. But I'm sorry, I don't have very good hearing. So, but if I've interpreted your question correctly, you're asking why can't we do it all in real time?
Yeah,
Is that right?
If we can do it offline to get the high resolution image
Yes.
offline,
Yes.
why do we have to do it in real time?
Right.
Because
So
it's quite complicated and expensive.
yes. Yes. So I think it's fair enough to say that the geometric wavefront sensor in the TP3 is more effective using the higher order aberration rather than the low order aberration. So if you could remove the low order aberration in real time, then you're going to get a much more effective use as far as the high order is concerned, using the geometric wavefront sensor in the TP3. So that's the reason. There is some form of interaction which we are not sure why, but we need to remove the tip and tilt first before we can actually get the performance on the higher orders. So that's why we're doing that.
I was wondering then, you take an image, if I understand correctly, every 1/6,400 seconds. So how much data do you take every night?
It's considerable. It's not that high a frame rate at this stage, so we're only up to 100 frames per second currently, as far as our tests are concerned.
Okay.
So we're not, because it's low order that we're removing in real time, we can close the loop at say 200 hertz for the tip tilt. But for the higher aberration, we obviously need to increase the frame rate to a much higher frame rate.
And then, if I understand correctly, you do a second-order Zernike polynomial fitting and interpolate?
Yes.
And how long does that take to process for one night of data?
It's considerable, but all we're wanting is effectively an extended object as it passes through a field of view. We don't need to view an object continuously. We basically, with space situational awareness, we want to basically find that object and capture that object as it's moving at high frame rate within that field of view. What we could do then is slew the telescope to the new region and then take another series of images, particularly for LEO. I mean, that's what we need to do for LEO. For GEO, you basically turn the guidance system off, and effectively you have star trails going across. But our focus is going to be on LEOs rather than GEOs. And so it's really just basically taking a snapshot or a series of snapshots, tracking at the sidereal rate, and then possibly moving or slewing the telescope to another region where you have a wide field, and then you then collect the data, but also correct in real time, and then you move again to another region, etc. But the idea is just basically to get an idea about what the extended object looks like. For example, if there could be a solar collector that's effectively bent, or it's fallen off, or something has happened to it. That's the information that we really need.
And just for the sake of getting a concrete figure,
yep.
If you have 1 hour of data under your typical conditions, is that then 5 hours of computation, 10 hours a week? How much?
I would say at least that, probably more.
Sorry?
Probably more.
Probably more than a week.
Yeah.
Okay.
Yeah.
Thank you.
Yeah, pleasure. Thank you. Hi.
So, how's the angular size of a CubeSat on the sky? Have you estimated the angular size of a CubeSat on the sky?
Yes, we have. It's sub-pixel.
Is?
It's sub-pixel. It's less than a pixel.
Less than a pixel.
Less than a pixel.
And in angular size?
Yeah.
Have you estimated it? In angular?
The number?
In angular size? In arc seconds?
Arc seconds? I don't have that information with me, but it's pretty small.
It's very small.
Using the telescopes that we're using, which is either a 0.6 at prime focus or the 1 meter. The one way, of course, in order to improve and to actually then be able to image and see something other than sub-pixel would be to have some form of magnification in terms of an eyepiece. So that would be something, but that's much more challenging because that puts the emphasis then on the telemetry.
Yeah, my question was in that direction because what I think is probably 60 centimeters telescope is too small.
Yep.
To be able to solve that smaller angular, tiny angular resolution.
Yes.
Okay.
That's another problem. We're just taking tiny steps for the time being.
Hello.
Hi.
I wanted to ask you about who would affect a based CNN in means of computational, costs.
Yes.
Would you afford it? Could you?
Yes, definitely. Yes.
But
yes.
it would introduce an error or something about, it means.
Well, we've actually developed not a CNN, but a reservoir computer in real time, so we can actually have processed in real time and solve some of these problems without having to use a CNN.
Oh.
So we've actually run, and just if you haven't heard of reservoir computing, effectively it's a recurrent neural network And with the recurrent neural network, we're actually using time series data, and we're tracking time series of each of the Zernica polynomials. And effectively, we're feeding that information into a reservoir computer that effectively then provides that. I could go back to it, but there's a schematic that I had before where basically it's then deriving an output based on that neural network, which is the spatially variant point spread function. So to answer your question, yes, we could use a convolutional neural network rather than that, but we have expertise in reservoir computing. Yeah. Thank you.
Well, then we'll finish this talk.
Thank you.
Thanks to the speaker.
Thank you. Thank you very much. Thank you. Before I close, I'd just like to thank Alex for all his kindness and the kindness of the whole group, actually. It's been fantastic being here, and I feel quite privileged, actually, particularly going across to Opama last night and yesterday. It's been fantastic, so thank you very much.
Thank you.
Okay,
Thank
good.
you. So there will be coffee in the scientific coffee now in the cafeteria.
Oh, thank you. Appreciate that.